Okay, so good evening everyone. I am Shivani Dhok and I take the tutorial for the course of Digital Signal Processing and its applications every Friday. And I welcome you all for the week 5 tutorial of this course. So, like every week, this week's tutorial will also be divided into two parts. One will be a quick recap of week 5 content, followed by the questions which are related to this week 5 content. Now, this particular week 5 introduced a very important transform that is known as Z transform. So, let me have a quick recap of the concepts that were introduced for this Z transform in this week. If you have any queries, you can stop me at any point and ask. No need to wait till the end of the session. Let's clear it then and there. Another thing, if you have, if at any point of time my screen freezes or you're not able to see what I'm writing, just quickly unmute yourself and ask. I may not be able to see the chat box, so it will help me out in figuring out what exactly is the issue. Okay, so let's start with today's recap. So as I mentioned, we introduced a very important transform that is known as the Z transform. Now the Z transform is for discrete time signals. And let's say we have a signal x of n. This is a discrete time signal and its Z transform is x of z. So this x of z is given by summation and running from minus infinity to infinity x of n into z to the power minus n, where this z here is equal to r into e power minus j omega, e power j omega, sorry. So this entire equation is like finding DTFT. So this is equivalent to finding DTFT of x of n into r to the power minus n. So this gives it like a tapering kind of structure, which helps which helps us to analyze this particular signal at least in a particular range of this r. Another important concept associated with this Z transform is its region of convergence. So this region of convergence is the values of Z, or rather to be very precise, this is set of the values of Z for which x of Z converges. So when we are defining the Z transform of a particular signal, it is mandatory to give both the things. One is the expression for this x of Z and another is its region of convergence. So this x of Z along with the region of convergence is a unique thing for a given particular signal. It's a given x of n. It might happen that two different signals have same value of this x of Z, but their region of convergence are different, which means their Z transform are different. So a Z transform has to be completely characterized by this along with its region of convergence. So that is a very important thing that we need to keep in mind. So if you have been asked to find Z transform of a particular signal and you just write this expression, it is meaningless. You need to tell in which region of Z or for what values of Z it is true. After that, we looked at or we figured out how to find the inverse Z transform. We said that finding it using exact equation is difficult. So what we will do is we will use Z transform of standard signals and use them. standard signals. We will use the Z transform standard signals to find inverse Z transform by observation. And for that we said, okay, let's stop here only. We'll discuss how to find it afterwards. Next important things that we looked at was the properties of the Z transform. So for this, let's say x1 of n is a signal with Z transform as x1 of z with ROC R1, and x2 of n is another signal with Z transform x2 of z with ROC R2. Then the Z transform follows certain properties. The first property is the linearity property. So this property says that if I have linear combination of my signals, that is alpha x1 plus beta x2, then its Z transform is given by alpha x1 of n, x1 of z plus beta x2 of z with ROC at least R1 intersection R2. This is linearity property. Next property is the delay or shift property. So it says that if I shift my signal, let's say x1 of n, by a value n naught, that is, if I want to figure out what is the Z transform of this signal, x1 into x1 of n minus n naught, then its Z transform is given by z to the power minus n naught into x of z, and its ROC remains R1, and maybe some changes at z equal to 0 or plus minus infinity. Okay. Another property that we looked at was differentiation property. So what it says is the signal n into x of n, or let's say x1 of n, has a Z transform minus z d dz of x1 of z. This is one here. Yeah. So it says that if I differentiate my Z transform and multiply it by minus z, then its inverse Z transform is given by n into x1 of n, and the region of convergence again is R1, and some changes same as whatever happened here. And the last important property that we looked at was convolution property. So it says that if I have x1 of n convolved with x2 of n, so if I am having convolution of two signals, that is x1 of n and x2 of n, and if I find its Z transform, then the Z transform is given by x1 of z into x2 of z with region of convergence as at least R1 intersection R2. Next we said, so these are the properties of Z transform. Then we said that for an LTI system, what I can have is my y of n. So it's like this. For an LTI system, output y of n is given by x of n. So this is my input convolved with h of n, and this h of n is impulse response. So the Z transform of this y of n is given by y of z, which is equal to x of z into h of z. So what we can say is, from this equation we can say that this h of z is y of z divided by x of z. So this particular quantity here is known as system function or transfer function. Now this particular thing h of z, which is equal to y of z upon x of z, if the numerator is a polynomial in z inverse or z for that matter, and this denominator also is a polynomial in z inverse or z anything, then such a transfer function or such a system with such kind of transfer function or system function is known as rational system. Two important things about this rational system is roots of numerator polynomial are known as zeros. Just a minute. Okay. And the roots of denominator polynomial are poles. Okay. So these zeros and poles are very important, and we will see the importance of both of these quantities in a greater detail in coming time. Just a minute. Okay. And in order to okay, so this is what we know call as the rational system, and in order to find the inverse of the rational systems or inverse Z transform of this particular rational system, what we use is something known as partial fractions. This concept is taught well in your maths courses. However, if you get confused or if you have any questions, just quickly revise it once. So what this partial fractions do, so we try to write this h of z as finite series finite series of z inverse and z plus sum of proper fractions, a proper rational function. So what do we mean by a rational function? It means that the degree of numerator polynomial is less than the degree of denominator polynomial. So we write it in this form and then use the Z transforms of the standard functions to find out the inverse Z transform. So this was all that was covered in this first week. Another thing I forgot to mention here is the nature of this region of convergence. Maybe I should write it somewhere. Okay, so yeah, let's write it here. So this region of convergence is always of the form of annular rings, circles, like interior or exterior of the circles. So let me write it. Region of convergence or ROC is of the form of so this ROC is of the form of um, annular rings interior of circle or exterior of some circle. This particular point, if it is not clear at this moment, it's okay. In the coming slides, I have an example that will show this kind of structure of our region of convergence. Okay, so that's all about the recap. If you have any questions regarding any of this concept, then let me know. Otherwise, I'll move on to the um, examples that I wanted to cover today. Okay. Okay, if there are no questions, then let's start with the first question that I have planned. So these are the questions from last year's assignment. So let's start. Let f of n comma k. So the question says, let f of n comma k be defined as like this. Which of the following sequences have the DTFT? Or which of the following sequences we can find the DTFT or DTFT exists? So what is the condition for the existence of DTFT? So DTFT exists when the signal is absolutely summable. Okay, so what does it mean? If x of n is my signal and I want to find DTFT of this signal, which is x of omega, then mod of x of omega is finite if summation n running from minus infinity to infinity magnitude of x of n is less than infinity. This particular condition we had seen last week also. This particular condition here means that that particular signal x of n is absolutely summable. So now what is asked to us? We are given a set of functions, that is f of n comma k, which take up this form. And for all of these values or all of these given subparts, we need to figure out if DFT of this particular signal exists or not. Okay, so let's start with the first one. So let's start with this one. Okay, so what it says that we have x of n, and this x of n is basically what's happening. Okay, yeah, so we have x of n, which is equal to f of n comma minus 1 comma 1. So now if we look at the definition, here our k is minus 1 comma 1. So this x of n is equal to k, that is minus 1 comma 1 to the power n into u of n. Okay, so this is our signal. So now let us check that absolute summability. So n running from minus infinity to infinity, magnitude of x of n, which is equal to summation n running from minus infinity to infinity. Magnitude of minus 1.1 to the power n is simply 1.1 to the power n into u of n. Now this u of n is non-zero only for n greater than or equal to 0. So therefore this now summation becomes n running from 0 to infinity 1.1 to the power n. Now if we observe, this is an infinite geometric progression or IGP with first term as 1 and common ratio as 1.1, which is greater than 1. And therefore, this diverges, which means that this is equal to infinity, or this tends to infinity, which means that this x of n is not absolutely summable, which means DTFT does not exist. Is it clear? Any problem in this particular question? Okay, so let me
why do you take
sorry?
off that minus sign, ma'am? Why do you take off that minus sign? 1 - 1.1, ma'am.
So I have this minus 1.1 to the power
Okay,
n.
magnitude, modulus. Okay, modulus. Okay, thank
Yeah.
you. Modulus.
Yeah. Yeah.
Modulus value.
Yeah. Okay. Any other questions?
No, ma'am. No, ma'am.
Okay. Yeah. So let's move on to the second part now. So this is the second part. So here it is said that this x of n is f of minus n comma minus 1.1. Okay. So now this is again like this. So now here my k is minus 1.1. Same thing, but now instead of n I have minus n. So wherever I have n here, I need to replace it by so wherever I have n here, I need to replace it by minus n. So how does it look? My k is minus 1.1 to the power, replace n by minus n, so it will be minus n into u of minus n. Okay, now let's check the same thing. So we need to check summation n running from minus infinity to infinity, magnitude of x of n, which is equal to summation n running from minus infinity to infinity, magnitude of minus 1.1 to the power minus n into u of minus n. Okay, so now this u of minus n, so this thing u of minus n is non-zero when my minus n is positive. That is this u of n is equal to 1 for n less than or equal to 0, and is equal to 0 for n greater than 0. So this is just flipped version of our unit step function. So now this limits will become from minus infinity to 0. And since we have a mod sign here, so we'll just keep the magnitude. So now we have summation n running from minus infinity to 0, 1.1 to the power minus n in like this. Now what we will do, let's do this. We will replace. So what we will do, we'll substitute m as minus n, which means now my m will also vary from 0 to infinity. So therefore summation n running from minus infinity to infinity, magnitude of x of n becomes summation n running from 0 to infinity 1.1 to the power n. So this is exact same summation that we had in our previous question, which means that this also goes to infinity. We have seen this in last part. Which means that this particular x of n is also not absolutely summable. which means DTFT does not exist. Now let us repeat the same thing for the last part. So this is our last part. So here x of n is f of minus n comma 0.9. So here our k is 0.9 and again n is replaced by minus n. So what we get is 0.9 to the power minus n into u of minus n. Okay. So therefore summation n running from minus infinity to infinity magnitude of x of n is equal to summation n running from minus infinity to infinity 0.9 to the power minus n into u of minus n. Now here again we have this u of minus n thing, which is non-zero only for minus infinity to 0. So again the summation that we have now is n running from minus infinity to 0, 0.9 to the power minus n. Now same trick we will use, we'll substitute m as minus n, which means this m varies from 0 to infinity. So therefore summation n running from minus infinity to infinity magnitude of x of n is equal to summation n m running from 0 to infinity 0.9 to the power m. But now this is an infinite geometric progression with first term as 1 and common ratio as 0.9, which is less than 1. So therefore this converges and is given by 1 upon 1 minus 0.9. So first term divided by 1 minus common ratio. So this comes out to be equal to 1 upon 0.1, which is equal to 10, which is less than infinity. So this is finite. So this is giving me a finite value, which means that it is absolutely summable. Which means DTFT exists. Is it clear? Any questions? Okay. If not, then let me move on to the next question. Okay, so this question says that we know that the Z transform of a to the power n u of n is 1 upon 1 minus az inverse with region of convergence magnitude of z greater than a. We know, so a here is a positive quantity. We now we need to find another sequence with same Z transform but with ROC magnitude of Z less than a. Okay. So what is said to us is the signal a to the power n u of n has Z transform as 1 upon 1 minus az inverse with region of convergence magnitude of Z greater than a. Now we want to find x of n, which we don't know, with same Z transform but with ROC magnitude of Z less than A. Exactly opposite ROC. Okay. So in order to find that, let us look at this particular series. Okay. Yeah. So what we'll do is let us observe 1 upon 1 minus A Z inverse when magnitude of Z is less than A. Now let us try to figure out straight away from this particular thing, this particular kind of way it is listed. So we have 1 upon 1 minus A Z inverse. Now here what we can see is this is like an final expression, or let's say final solution, or some series solution of an infinite geometric progression where this numerator is common first term and this denominator is common ratio. Okay, so in that situation we can write this 1 upon 1 minus A Z inverse as 1 plus A Z inverse plus AZ inverse square and so on. But this equality, this is valid when magnitude of AZ inverse is less than 1, or A into magnitude of Z inverse is less than 1, or magnitude of Z is greater than A. Now, but for our case, magnitude of Z is less than A. Okay, which means that the series will diverge, which means that this is a bad option to analyze this kind of system, the series, this particular Z transform in this way. This is a bad option to analyze this in this way. Now this is not working, we understood. Now let us try to massage this signal and bring it to some another way, or try to represent it in some another way. So what we will do is, let's take this, let's say that this is x of z, which is 1 upon 1 minus AZ inverse, and let's multiply and divide it by Z by A. So what we will get, in the numerator we will get A inverse Z, and in the denominator what will we get? We'll get ZA inverse minus 1. Now let us, so this we can also write as minus A inverse Z upon 1 minus A inverse Z. Okay, now just focus on this part. Forget whatever is there on right hand. Forget this negative side, and just focus on this part. Now this part is again like so what is this? Yeah. So this is also like an infinite geometric progression solution, but first term as A inverse Z and common ratio as A inverse Z. Now here, so we can write this as minus, and inside the bracket A inverse Z plus A inverse Z whole square and so on till infinity. So again, as we discussed earlier, this equality holds when does this hold? This holds when magnitude of A inverse Z is less than 1, or magnitude of Z upon A is less than 1, which implies magnitude of Z is less than A. Okay, so this is working for us. This particular thing is working for us. Now we want to find out the signal which gives us this transform. So now in order to get that, we'll focus on this series form. Okay, so what we have got? We have got x of z as minus of A inverse c plus a to the power minus 2 z square plus a to the power minus 3 z cube and so on. Okay. So this we can write as minus of summation n running from 1 to infinity a inverse z to the power n. Okay. So this is what we are having. So this is A inverse z to the power 1 plus A inverse z to the power 2 and so on. So like this we are getting. So we can separate, or what we will do here is, let us do this. Replace or substitute m as minus n, which means that m will vary from minus infinity to minus 1. So therefore x of z is equal to minus summation m running from minus infinity to minus 1 A inverse z to the power minus n, which we can write as minus summation m running from minus infinity to minus 1 a to the power n into z to the power minus n. Okay, now you look at these limits. This is valid from m running from minus infinity to minus 1. So now you consider this particular signal. So, or in other way, this getting this kind of thing is equivalent to writing this as minus of summation m running from minus infinity to infinity yeah, a to the power m into z to the power minus m into some function of m. So this g of m is 1 for m less than or equal to minus 1, and it is 0 otherwise. So how does this g of m look? This g of m looks something like this. This is 0. This is m. This is g of m. So it is 1 from all the way to from minus infinity. This is minus 1, and then it is 0, minus 2, minus 3, and so on. And then it is 0. So this looks something like a flipped and shift version of unit step function. Okay, this is 1. Magnitude is 1. So this looks something like a flipped and shifted version of unit step function. So now let us try to get this particular thing from a unit step function. How does a unit step function look? So this is our unit step function. This is m, u of m, 0, 1, 2, and so on. So it is 1 here, and it is 0 for all the negative values. So now let us look at u of minus m. So it will be 1 here, and for all the negative values, but it will be 0 here for all the positive values. Now, one small difference, subtle difference here is this thing. So here the non-zero values start from -1, here it starts from 0, which means that we need to shift it this leftwards by 1 unit, which means that in order to get this, we'll have to shift this signal rightwards by 1 unit like this. That is u of -m minus 1. So now what we will get is, we have m here, this is 0, we have 0, 0, 0, 0 everywhere on the positive side, and 1 only for the negative values, and so on. So this is exactly same. So from this, what we observe is, this g of m is simply u of -m minus 1. Okay, now let me substitute it back to my x of z formula. So therefore, x of z is equal to summation. Now I'll simply replace my m by n. So n running from -infinity to infinity, a power n u of -n minus 1 into z to the power -n, which I can also write as summation n running from -infinity to infinity minus of a power n u of -n minus 1 into z to the power -n. Now let us compare it with the definition of Z transform. So that gives me, so the definition is basically x of z is equal to summation n running from -infinity to infinity x of n to z to the power -n. So now if we compare this part here and this part here, is exactly the same thing. So we are simply comparing the coefficients of these two equations. So from comparison, what we get is x of n is equal to minus a power n into u of -n minus 1, and we've got this from its z transform, that is 1 upon 1 minus a z inverse, but with ROC as magnitude of z less than a. Okay, is it clear? Any questions? Okay. So the main key takeaway from this particular question is the Z transform and region of convergence for two standard uh, signals, and those two things we need to remember. We need to keep them in mind. So as a summary, what we get is, if I have a signal a power n, sorry, small mistake. Yeah. If I have a signal as a power n into un, its z transform is given by 1 upon 1 minus a z inverse with region of convergence magnitude of z greater than a, or for that matter magnitude of a. Now another thing to keep in mind is, we found another signal which is minus a to the power n u of u of minus n minus 1, whose z transform expression is exactly the same, that is 1 upon 1 minus a z inverse, but a completely different ROC, which is magnitude of z less than a. These are two standard signals, and we will use the z transforms of these standard signals left and right to find the inverse z transforms. So we need to keep this in mind. Okay, any questions? If there are no questions, I'll move on to the next part. Okay. Okay, so here what is given to us is, let the Z transform of a signal be x of z 4 minus 2z inverse plus 4z to the power 2 plus 2z to the power 3 upon 1 minus z square, and its with region of convergence magnitude of z less than 1. What is what is x of n? So now what is given to us is x of z is equal to 4 minus 2z minus 4z square plus 2z cube upon 1 minus 2z square. Okay, so now just look here, these two things which I have highlighted in blue. I can take 4 common from these two, so I can write it as 4 into 1 minus z square. And similarly, if we look at these two things, that is this minus 2z and plus 2z cube, I can take out common minus 2z, that will give me 1 minus z square upon 1 minus z square. So what I get here is 4 minus 2z. Okay, so we have 4 minus 2z here. Now we need to find the inverse z transform of this signal. Okay, so now in order to figure out what z transform this has, I will introduce the z transform of another important signal, that is the unit impulse. So now if I have a unit impulse signal here, its z transform is given by summation n running from minus infinity to infinity delta n into z to the power minus n. Now the z to the power minus n will pick up that value of n at which this impulse is located, and this impulse is located at n equal to 0. So this is equal to summation n running from minus infinity to infinity delta n into z to the power minus 0, which is simply 1. Okay, so and this summation here, that is summation n running from minus infinity to infinity delta n is also 1. So we are just simply adding impulse over the entire range. So therefore what we get is the impulse response of delta z, or unit impulse function, is constant 1. Now if I multiply it by a constant value, then again its z transform will be a constant, and this is coming from the linearity property. And if I shift it by this, so for this we will use the time shift property. And what does the time shift property say? It says that if I shift a signal x by n naught, then the z transform is given by z to the power minus n naught into x of z. Okay, so therefore here what we get is a into z to the power minus n naught. Okay, so now let us write what we have. We had x of z as 4 minus 2z inverse. Sorry, 4 minus 2z, like this. Now this particular thing here, this 4 is like a constant. So this 4, so if I have my a equal to 4, then its inverse z transform will be a into delta n. So if I take inverse z transform, then that of this 4 will be simply 4 into delta n minus, so again here we are using linearity property. minus 2z inverse 2z. Now here if you compare this, so for this particular thing our a is 2 and my n naught is minus 1. So therefore if I take the inverse z
Not
transform, then
4, ma'am.
sorry,
A is A is 4, not 4. A. The value of A is 4, right, ma'am?
just a minute, can you please just give me 2 minutes, someone is there on my door. Just
Okay.
2 minutes. Yeah.
Mm.
Yeah, sorry for that disturbance. Yeah, you were asking some question.
Ma'am, A is 4, ma'am.
Okay, so what, okay, I got your problem. So if you consider this part, okay, wait, let's do it in this fashion. So I have this x of z as x1 of z plus x2 of z. Okay, and here my x1 of z is this 4, and this x2 of z is, or let's say minus, is 2 into z to the power z. Okay, now you just focus on this part and compare it with this. So you just compare this and this, make it of same color. Okay, so for this particular thing, if you look at this and this, the value of a is 4. So for finding inverse z of x1 of z, only a is equal to 4, and therefore its inverse z is given by 4 into delta n. Now you focus on this part. Okay, and x2 of z. Now only focus on this, forget what a was there for x1 of z. Now if you compare this thing and this thing, now here my a is equal to 2
Okay.
and n
Okay.
not equal to minus 1, and that's why its z inverse will be given by a into delta n minus n naught. N naught is minus 1, so minus of minus plus 1. Okay, so therefore my final x of n will be z inverse of this, z inverse of this plus z inverse of this by linearity property. So we will get 4 minus 2 times delta, sorry, 4 into delta of n minus 2 into delta of n plus 1. Is it clear now?
Okay.
Does it answer your question?
Yes, ma'am. The two parts you have split into two
Exactly.
parts. Okay. Okay.
Yes. Yes.
Mm, mm.
Any other question?
No, ma'am.
Okay. So the main key takeaway from this particular question is the Z transform of unit impulse. Okay. So this also you need to, what do we say, memorize. Yeah. And just a suggestion, when you are done with asking your questions, please unmute yourself. When you have question, just sorry, when you don't have any question, just unmute yourself. When you have questions, unmute yourself and ask freely. Yeah. Okay. So if there are no questions, then let me move on to the next question. So here, one of the question says that one of the important properties of the Z transform is n into x of n, and its Z transform is given by minus z into ddz of x of z. Now what we need to do is we need to compute the inverse Z transform of this given signal. Okay, so this looks weird why this has been listed and suddenly I have this x of z. Little bit weird it looks. So okay, so what we can do here is we will try to build this, or we'll try to get this x of z from, let's say, Z transform of unit step function. So for that, we should know what the Z transform of unit step function is, then only we can think in that direction. So here, since we are seeing this kind of question for the first time, I am telling you that this is somehow related to the Z transform of unit step function. So let us first figure out what is Z transform of unit step function. So we have u of n, and let's say its Z transform of u is u of z. So this u of z is summation n running from minus infinity to infinity u of n into z to the power minus n. Now this thing here is non-zero only when u of n is non-zero, and u of n is non-zero only for n equal to 0 to infinity. So this becomes summation n equal to 0 to infinity. In this region, u of n is 1, z to the power minus n. So now this becomes 1 upon 1 minus z inverse for magnitude of z, sorry, for magnitude of z inverse less than 1 or magnitude of z greater than 1. So now if you observe closely, this is the exact region of convergence given to us in our question. Okay, now let us do this. Now what we will do is, so this is our u of z, which is equal to 1 upon 1 minus z inverse. Now I'll write this as z upon 1 minus z inverse. Sorry, z minus 1. So now let us differentiate this. So what do we get? We get z minus 1 into derivative of z, that is 1, minus z upon z minus 1 square. This z gets cancelled, and what we are left with is minus 1 upon z minus 1 square. Now let me multiply by minus z on both the sides. So therefore minus z into d dz into u of z, this comes out to be as z upon z minus 1 square. Now this thing I can write as z upon, I can take out minus sign common, 1 minus z whole square. This is equal to z upon minus 1 square into 1 minus z square. So now this minus 1 square is again 1. So therefore what we get is minus d dz of, sorry, minus z into d dz of u of z, which comes out as z upon 1 minus z whole square for mod of z greater than 1. Now let us go back to our question. So in our question, what was given to us? X of z as z upon 1 minus z whole square for magnitude of z greater than 1. So this is the exact thing that was asked to us. So therefore, my x of z comes out to be equal to minus z into d dz u of z with magnitude of z greater than 1. And we had been given another important property in that particular question, that n into x of n is, for any signal x of n into x of n is minus d dz of x of z. So now here we have, if I take inverse z transform, so I'll have x of n which is equal to inverse z transform of this signal, and the inverse z transform of this signal will be simply n into u of n. Why? Because u of n had z transform of u of z, then n into u of n will have a z transform of minus z d dz u of z. So therefore, using this property, my x of n comes out to be equal to n into u of n. Is it clear? Any questions? So we need to know the z transform of some standard signals like impulse, unit step, sine, cosine, and those exponential forms, that is a power n un and minus a to the power n u of minus n minus 1. Okay, and if we know that, when you practice, when you solve questions, you yourself will get used to, and you will understand at what point we can apply those properties. Obviously, when you're seeing these questions for the first time, it will be difficult, but once you solve, once you practice, it will be easy for you to understand these kind of things. Okay, any questions till this point? We are running out of time. Okay. Okay. If we don't have any questions, then let's move on to the next question. So this question says that how many different regions of convergence could correspond to x of z if x of z is this particular transfer function? Okay, so we are given x of z. Since the font is small, let me write it. X of z as 1 minus 1 by 4 z inverse divided by 1 plus 1 by 4 z inverse into 1 minus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. Now let us just focus on this part. Okay. So this particular part here, 1 minus 5 by 6 z inverse plus 1 by 6 z to the power minus 2. So this is equal to 1 minus 1 by 3 z inverse minus 1 by 2 z inverse plus 1 by 6 z to the power minus 2. So we can write this 5 by 6 as 1 by 3 plus 1 by 2. So what we get is 1 minus 1 by 3 z inverse. We can factorize it to get 1 minus 1 by 3 z inverse into 1 minus 1 by 2 z inverse. Okay. So now we can substitute this back in our x of z equation. So therefore, x of z is equal to 1 minus 1 by 4 z inverse upon 1 plus 1 by 4 z inverse into 1 minus 1 by 3 z inverse into 1 minus 1 by 2 z inverse. Okay. So now in order to figure out the different regions of convergence, what we will do is we'll make use of pole zero plot. So what does pole zero plot mean? It means that it is a plot in which my x-axis is real part of z, y-axis is imaginary part of z, and then on that I'll plot my poles and zeros and unit circle and figure out what all sorts of region of convergence I can get. So for that, first we need to know what are the zeros. So for zeros, set numerator equal to 0. So therefore 1 minus 1 by 4 z inverse equal to 0, which means that 1 equal to 1 by 4 z inverse. Therefore z comes out to be equal to 1 by 4. Similarly, next we need to figure out what are the poles. So for poles, set denominator equal to 0. Okay. So for that we can set, so that will give us 1 plus 1 by 4 z inverse into 1 minus 1 by 2 z inverse into 1 minus 1 by 3 z inverse as 0, which means that each of these quantity or one of these quantities can be 0. So we can have 1 upon 1 plus 1 by 4 z inverse equal to 0, which means that my z is equal to minus 1 by 4 is a pole, which imply another thing is 1 minus 1 by 2 z inverse equal to 0, which means that z equal to half is also one of the pole, which means that 1 minus 1 by 3 z inverse is equal to 0. So z equal to 1 by 3 is also a pole. Okay, so this is what we are having here. So now let us plot this as on a pole zero plot. So now we have 0 as 1 by 4 and poles as minus 1 by 4, 1 by 2 and 1 by 3. Okay. Yeah, so let's plot this. So for that, let me draw this. Let me make this on one side. Yeah. So the first let's say this thing here is 1 by 2. Then I'll have 1 by 4 exact half and 1 by 3 somewhere here and 1 by 4 I'll have here minus 1 by 4. So I have a pole at 1 by 4. So poles, sorry, zeros we represent by O and poles we represent by cross. So we have a 0 at 1 by 4 and we have poles at 1 by 3, 1 by 2 and 1 by and minus 1 by 4. So this region of convergence are of this form: magnitude of z less than or equal to something, magnitude of the z less than or equal to something, greater than or equal to something. So this is my imaginary part of z and this is my real part of z. So if I'm talking about magnitude, magnitude means a circle in this particular plane. So if I draw a circle here like this, then this thing will have a radius of the magnitude of any point on that circle. Okay, so now let's say I have one circle like this, then I have a circle that passes through 1 by 3. So we had seen this in our class also, that the Z transform will be of this form, and then we have this R by R Z equal to half circle like this. So now I have three options of my four options of my uh, region of convergence. The only thing that we need to keep in mind is the region of convergence does not include the poles. So one option is anything in this region is possible. excluding 1 by minus 1 by 4. So this is possible. So what is this region? So the first region that we have is magnitude of z less than 1 by 4. So all possible annular rings and all possible interior and exterior of the circle such that no poles are included can be considered. Another option is this annular ring. Okay, so this region is a magnitude of z which is greater than 1 by 4 but less than 1 by 3. Now one subtle point, why can't we take this entire region? We can't take this entire region because this particular pole will be there in the region of convergence, and poles can never be in the region of convergence because at poles my denominator becomes 0, which means my entire z transform will go to infinity, means it will diverge. So poles cannot be in the region of convergence. So if I consider this entire red color shaded region as my region of convergence, this pole at minus 1 by 4 will be present. So we can't have such kind of region of convergence. Okay. Next option that we have is this. Like this. So for this, don't include the line shaded part that is gone outside. So the third region that we have is magnitude of z that is less than 1 by 4 but greater than, sorry, what did I write? Yeah, greater than half. Oh, I have written in everything ulta. In 1 by 3, 1 by 3 is smaller. Yeah, this region. And the last option that we have is this one, that is anything outside this part. So this one, the fourth region that we have is mod of z greater than half. In all of these region, if you look carefully, in none of them you will have what do we say, zero poles. So when you are given any particular transfer function and asked to figure out what kind of region of convergence you can expect, so you can look at all the possible annular rings that lie between two poles and interior to the innermost circle and exterior to the outermost circle. So this is a small trick that you can use if you want to find. So all the possible region of convergence will be interior to the innermost circle, exterior to the outermost circle, and other options will be the annular rings. So this kind of donut shapes that you're getting now, these are known as annular rings. So these kind of shapes or these kind of rings between any two poles. And be careful that you can't have poles in your region of convergence. You can have zeros. So if I would have had a zero here, it was okay. I can include zeros in region of convergence because they are making my z transform 0. They are not shooting it to infinity. So my series is not diverging there. So that's why zeros can be there in region of convergence, but poles cannot be. Is it clear? Any questions? Okay. Okay. So let's move on to the next question then. Next question says, what will be the Z transform of the signal x of n equal to half to the power mod magnitude of n. So now this can be written in two form for two cases. One, when my n is greater than or equal to 0, and another when my n is less than 0. So when our n is greater than or equal to 0, then magnitude of n, so here my magnitude of n is equal to n. So what we get here is 1 by 2 to the power n. And for the case when n is negative, magnitude of n is minus n. So what we get here is 1 by 2 to the power minus n, that is 2 to the power n. Okay. So now if you observe carefully this part, so this is like 1 by 2 to the power n into u for value of n greater than or equal to 0. And we had seen that for this particular kind of thing, when we are having something like this, that is n greater than or equal to 0, we can write this as 1 by 2 to the power n multiplied by a signal that is valid in this region only, or is equal to 1 in that particular region, that is u of n. So this yellow shaded region we can equivalently write as different color. This we can write as 1 by 2 to the power n into u of n. Similarly, if you look at this part, this 2 to the power n, this 2 to the power n for n less than 0. This is exactly similar case which we had for a to the power n for n less than 0. So this particular thing, this region can be captured by u of minus n minus 1. We have seen this earlier. So therefore, this I can write as 2 to the power n into u of minus n minus 1. Okay. So therefore, what we can see is this particular thing is valid for n greater than or equal to 0. This particular thing is valid for n less than 0. And this x of n is basically equal to this and this particular thing. And we can write this as addition of these two signals which don't overlap in time domain, which are region wise. So what is happening is my x of n is defined on the entire n region. Then this is minus 1, this is 0, this is 1. Then this is the region in which this 2 to the power n into u of minus n minus 1 is defined. And this is the region in which 1 by 2 to the power n into u of n is defined. So my x of n can be written as addition of this signal and this signal. Okay. Okay. So now what we get? We get x of n as 1 by 2 to the power n u of n plus 2 to the power n u of minus n minus 1. This we can write as 1 by 2 to the power n u of n minus of 2 to the power n u of minus n minus 1. So do you recognize these in standard forms? So if we look at our second question which we had seen, this one, so that both of these signals are in that standard form. Let me copy this. Like this. Yeah, just for reference I'll keep it here. So if you observe carefully, this is our first standard form, that is a power n un. So if you observe this part, first part, so this is equal to a power n u of n with a equal to half and magnitude of a is less than 1. Okay, so this is what we are having here. Sorry, a as half. So then this particular thing will have z transform as 1 upon 1 minus a z inverse, 1 upon 1 minus a z inverse, and with region of convergence, magnitude of z greater than a, that is greater than half. Okay, so this first part is done. Now you look at the second part, this part. This is like minus, this is equal to a minus a power n u of minus n minus 1 for a equal to 2. So now just focus on this. Minus a power n u of minus n minus 1. This has a z transform of 1 upon 1 minus a z inverse with ROC magnitude of z less than a, or less than magnitude of a. So this will have a z transform of 1 upon 1 minus, so here my a was half, 2z inverse with ROC magnitude of z less than a, that is 2. Okay, so now we can use the linearity property. So therefore x of z is 1 upon 1 minus 1 by 2z inverse minus 1 upon 1 minus 2z inverse with ROC as magnitude of z greater than half intersection magnitude of z less than 2. So therefore what we get is my x of z is 1 upon 1 minus 1 by 2z inverse minus 1 upon 1 minus 2z inverse with region of convergence magnitude of z which is less than 2 and which is greater than half. Okay, is it clear? Any questions?
Ma'am, I am missing one minus sign.
So we had plus 2 to the power n u of minus n minus 1, right? So that we wrote as minus of minus.
Okay.
Because in standard form we had this.
Okay.
Yeah, just to bring it to our known form, I wrote it as minus
Okay.
of. Yeah.
While calculating, I have missed the minus.
Yeah, it's fine. Okay. Okay, if there are no questions, then let me move on to the next question. So this says that consider an LSI system with Z transform of the impulse response as H of Z. H of Z is rational with M unique poles and K unique zeros. So we have H of Z. This H of Z has M unique poles and K unique zeros. Okay, then it is said that an input signal with Z transform X of Z that has n unique poles and no zeros is applied to get the output y of n. So we have X of Z, which is Z transform of the input. This has n unique poles and 0 unique zeros. Okay, so this we know. Now this gives an output y of n, and let's say y of z is the Z transform of that output. Another thing that is given to us is this X of z and H of z have a poles in common. So both of them have a poles in common, or let's say to be precise, a unique poles in common. Okay, how many unique poles will be there in the Z transform of y of z? Z transform of y, that is y of z. So now we know that y of n is x of n convolved with h of n, because it is given to us that we have an LSI system. So therefore this y of z will be given by x of z into y of z. Okay. So now what is happening is y of, sorry, what did I write? H of z. Yeah. So it was given to us is that this h of z has some number of poles and some number of zeros. It has m poles and k zeros, unique zeros. And this x of z has no zeros but n unique poles. Which means that if I multiply these two, uh, uh, the number of the poles thing will get multiplied. So for example, if my x of z is equal to z minus a into z minus b and so on, let's say like this, divided by z minus c into z minus d, something like that, just for example. Sorry, just let this be h of z, and my x of z be z minus a, sorry, no poles, no zeros it has, so 1 upon z minus e, like this. So my y of z will be equal to z minus a into z minus b upon z minus c into z minus d into z minus e. So what is happening here is this will take up zeros of h and poles of both x and h. So the number of unique poles that now we will have will be basically addition of m poles and n poles. But we are given that we have a unique poles. So now if I a poles in common. So if I am adding m poles plus n number of poles, then in this I am calculating this a common poles twice. So I'll have to subtract it. So therefore what we get is number of poles, or let's say unique poles, as m plus n minus a. Now, is this correct? My question is, whatever I spoke till now for this equality, is this equality correct? So now to understand this, let us take a simple example. Okay, so now let my x of z be given by 1 upon 1 minus 1 by 2 z inverse, 1 minus 1 by 3 z inverse. Okay, so now here, how many unique poles does this have? This has two unique poles. One is 1 by 2 and one is 1 by 3. So two unique poles, which means m is equal to 2. And let's say we have h of z as 1 minus 1 by 2 z inverse divided by 1 minus 1 by 4 z inverse into 1 minus 1 by 5 z inverse into 1 minus 1 by 3 z inverse. Now, here, how many zeros does it have? It has k equal to 1 zeros and n equal to 3 poles. And there is one pole in common. So 1 by 3 is the common pole. So therefore, a is equal to 1. Now, according to our answer, what should be the number of unique poles? According to our answer, that will be m plus n minus a, that is 2 plus 3 minus 1, that is equal to 4. Now let us get our y of z. So y of z is x of z into h of z. What is x of z? So this is equal to 1 upon 1 minus 1 by 2 z inverse into 1 minus 1 by 3 z inverse multiplied by 1 minus 1 by 2 z inverse upon 1 minus 1 by 4 z inverse into 1 minus 1 by 5 z inverse, and we had 1 minus 1 by 3 z inverse, so I'll just make this 2. Now this gets cancelled, so what we get is 1 upon 1 minus 1 by 3 z inverse 1 minus 1 by 4 z inverse into 1 minus 1 by 5 z inverse. So how many unique poles it has? So unique poles are 1 by 3, 1 by 4 and 1 by 5, which means that 3 unique poles. Is it what we got according to our answer? No, according to our answer it was 4, but now we are getting 3, which means our answer is wrong. Why is our answer wrong? Our answer is wrong because we are having a pole getting cancelled with a 0. If this pole 0 cancellation was not there, for example, if this was 1 by 7 instead of 1 by 2, then that wouldn't have cancelled with this. So our answer would have been 4. But now we are having a pole 0 cancellation. So if in case we have some poles completely nullified by zeros, we'll lose out on one pole, and that is happening in this kind of example. So therefore this thing here, what we wrote, this thing here is true when there is no pole 0 cancellation. But if there is pole 0 cancellation, we will get number of unique poles less than this particular value. So therefore we'll modify our answer little bit. So what we can do is we'll modify it little bit and we'll say number of unique poles is less than or equal to m plus n minus a, and this equality holds if there are no pole 0 cancellations. Is it clear? Any questions? This was also a question in last year's assignment. So yeah, these kind of questions do come in exam. Yes. Any questions?
Show, ma'am, show the key takeaways, that formulas, ma'am, unique, for unique is a transforms. Once again. Or can we have this slide shows somewhere else?
These slides will be shared with you once the lecture is done. In fact, you have the slides of all the lectures covered till now. It's there on the NPTEL portal. So if you don't take notes now, it's okay. You will have these slides with you.
Okay.
Yeah,
In
yeah.
down, where
You can.
exactly, ma'am?
So in your NPTEL portal, on the left hand side bottom, you will have problem solving session tab. Go to there. There will be a link for recorded sessions. There you can find them.
Okay.
Yeah.
Can we, ma'am, can I have your email ID, ma'am?
No, you can post your questions in that portal. The main reason of that is this video will go on YouTube and they will spam my email. So what you can do is you can post your queries in that question answer portal. You can mention the
Uh-huh.
private tutorial session in the subject. So I will open and respond to you.
Okay.
Yeah, that I can do.
Okay, ma'am.
Yeah.
The next day itself, we will get the answer, isn't it, ma'am?
Which answer?
Any questions if we post it, the next day we can get the
As
answer,
early as
reply like.
possible. As early as
Ah,
possible, I will answer you.
okay,
I
okay,
won't
ma'am.
commit the next day, but yeah, as early as possible, I will reply.
Okay.
Okay, let me finish off the content for today's lecture and then you can ask these non technical questions at the end. Okay, so let me take up this question. Yeah, determine the inverse Z transform of the following function for all possible choices of region of convergence. So now let us try to simplify this first. So the Z transform given to us is 1 plus Z inverse upon 1 minus 5Z inverse minus 6Z inverse. So this minus 5 in the denominator, we can write it as minus 6 plus 1. So we can factorize this. So we will get 1 minus 6Z inverse plus Z inverse minus 6Z to the power minus 2. So therefore we have 1 plus Z inverse upon 1 minus 6Z inverse upon 1 plus Z inverse, which is equal to 1 upon 1 minus 6Z inverse. So this is again a standard form. This is of the form of 1 upon 1 minus AZ inverse with A as 6. Now what are the possible region of convergences? So if we observe carefully here, the denominator, oh sorry, not here, this part, if you observe carefully, root or rather pole is located at Z equal to 6. So my region of convergence looks something like this. I have a 6 here. So this is what I have, yeah, like this. So one possibility is inside the circle. So I have a pole here. Let me mark the pole. So this can't be included in my region of convergence. So one possible region of convergence is this. So this region is magnitude of Z less than 6. And another option is this region. So this green region is magnitude of Z greater than 6. So these are the two possible regions or region of convergence. So let's do it one by one. So first thing is for magnitude of z greater than 6, x of z as 1 upon 1 minus 6z inverse. Again, let's go back to our standard forms. So these are our standard forms. I'll make its font a little bit smaller. So now magnitude of z greater than magnitude of a. This is the first part. Let me have proper color coding like this. So this is the exact same thing. So now if I observe carefully, so its inverse z transform will be a power n u of n with a as 6. So therefore x of n for this case is 6 to the power n u of n. Now second option is magnitude of z less than 6. And again I have x of z as 1 upon 1 minus 6z inverse. Now for this, we will look at the second standard form. So 1 upon 1 minus az inverse with ROC magnitude of z less than a. We have inverse z as minus a power n u of minus n minus 1. So for this particular region, x of n comes out to be equal to minus 6 to the power n u of minus n minus 1. Is it clear? Once you know these standard forms, solving these questions is very easy. Okay, if you don't have any other questions, let me move on to the next question then. Okay, so this question says, if the z transform of x of n is x of z, what will be the z transform of z naught x to the power n? So what is given to us is, we have x of n and its z transform is given by x of z, and by definition this is n running from minus infinity to infinity x of n into z to the power minus n. Okay, now we are given another signal. We are given x1 of n as z naught to the power n into x of n, and this z naught is not equal to 0, that is given to us. So now we need to figure out what is the z transform x1 of z of this signal. We are not getting how exactly these things are happening, or we can't observe and find some property that will help us out. So let's go back to the basic definitions. So x1 of z by definition will be summation n running from minus infinity to infinity x1 of n into z to the power minus n. This is equal to summation n running from minus infinity to infinity z naught to the power n into x of n into z to the power minus n. Okay, let me add a page. Okay, so this we can write as summation n running from minus infinity to infinity. First I'll write x of n, and then the z naught to the power n, what I'll do, I'll write it as z naught to the power minus 1 to the power minus n to z to the power minus n. Now by doing so, I can combine these two things, right? So now I can write this as summation n running from minus infinity to infinity x of n into z naught inverse z to the power minus n. This is our x1 of z. Now do one thing. Now compare this thing. I'll copy it for your reference on next slide. This thing and this thing. So if you compare, just compare the right hand side. This one and this one. So what you have, x of n and x of n is same. The only change is happening here. So now if I replace, or if I find x of z naught inverse z, then this will be equal to n running from minus infinity to infinity, x of n. Replace z by z naught inverse z. So that will be z naught inverse z to the power minus n, which is exactly equal to my x1 of z. So what do we get from here? So we have x1 of z as x of z naught inverse z. Is it clear? Is it obvious, or I need to explain it more? If you have any questions, then let me know. Okay, so if there are no questions, then let's move on to the last question that I wanted to cover today. Okay, yeah. Okay, so what is given to us is, let there be two signals, x1n and x2n, having z transform x1 of z equal to r0 upon r0 minus z, and with region of convergence r1, which is magnitude of z less than r0, and x2 of z as minus r0 by r0 minus 2z with magnitude of z greater than r0 by 2. And we want to determine the signal x3 of n, which is x1 of n plus x2 of n. And we need to figure out the ROC of this signal. Okay, so what is given to us is x. So we need to find the signal x3 of n, which is equal to x1 of n plus x2 of n. So the z transform of this signal will be x3 of z, which is equal to x1 of z plus x2 of z with region of convergence r1 intersection r2. And this is from the linearity property. And similarly, if I want to go from x1 intersection, x1z plus x2z to this side, or find inverse z, then that will be x1n plus x2n, and by linearity property, and this going in the opposite direction is only possible when this r1 intersection r2 is true. So let us first figure out what is r1 intersection r2. So our ROC is r1 intersection r2. Okay, and so basically this is at least. So this will increase if there is any pole zero cancellation. We'll figure out if there is any pole zero cancellation or not. So this R1 is magnitude of Z less than R0 by 2. And this R2 is magnitude of Z greater than, less than R0. And R2 is magnitude of Z greater than R0 by 2. So this is equal to magnitude R0 by 2 less than magnitude of Z less than R0. So this is the region of convergence directly. Now let us figure out if there are any pole zero cancellations or not. So for that, we have x1 of z plus x2 of z, which is our x3 of z. So let me write it ulta. So x3 of z was our x1 of z plus x2 of z with the above region of convergence. So this, okay, so this x1 of z is r naught upon r naught minus z plus, sorry, yeah, minus r naught upon r naught minus 2z. So let's cross multiply. We can take out r naught common. So we will have r naught minus z minus 1 upon r naught minus 2z. So let's get LCM and simplify things. R naught minus 2z minus r naught plus z upon r naught minus z upon r naught minus 2z. R naught gets cancelled, and what we are left with is r naught into minus z divided by r naught minus z into r naught minus 2z. Okay, so this is what we are having. So no pole zero cancellation, which means ROC is still magnitude of z less than r naught but greater than r naught by 2. Okay, so this is what we are having. So now this is true, and for this we can have a signal x3 of n, which is equal to x1 of n and x2 of n, where this x1 of n is simply the inverse z of x1 of z, and x2 of n is simply the inverse z of x2 of z. So let us figure out x1 of z and x2 of z individually, one by one. Okay, for that, what we have is x1 of z as r naught upon r naught minus z, and magnitude of z is less than r naught. Now let us try to bring this in our known form. We'll multiply and divide by minus z inverse. So what we get now? We get r naught into minus z inverse divided by minus r naught z inverse plus 1. So I can write this as minus r naught z inverse multiplied by 1 upon 1 minus r naught z inverse, and this magnitude of z is less than r naught. Now this part is equivalent to 1 upon 1 minus a z inverse with magnitude of z less than a, again our standard form, and this is the z transform of minus a power n u of minus n minus 1. Okay, this is okay. So what we have now is, so we have this thing here, 1 upon 1 minus r naught z inverse. So its inverse z transform is when in this particular region of convergence is minus r naught to the power n u of minus n minus 1. If I multiply, so now now I can take into account this minus r naught. So minus r naught upon 1 minus r naught z inverse. This has inverse z transform as r naught to the power n plus 1 into u of minus n minus 1. Along with that, I have a z inverse here. So I have minus r naught z inverse upon 1 minus r naught z inverse. So for this, we'll use our time shift property. So if y of n minus n naught has a z transform as z inverse y of z. So now we are doing ulta. We have this. So my y of z is basically this, and then we are multiplying it by a z inverse, which means for this y of z, this we have this y of n. So we need to shift this y of n by n naught, and here my n naught is 1. So then we'll have r naught replace every n by n minus 1, n minus 1 plus 1 into u of minus of n minus 1 minus 1. This gets cancelled. So what we are left with is r naught to the power n into u of minus n. This is the first thing that we have. So this is the value of x1 of n. So what we have x1n as r naught to the power n into u of minus n. So this is the first equation. Now we have x1 of n. Next we will find out x2 of n. So for that, let us focus on y2 of we have x1 of, now we need to figure out x2 of n. For that we have x2 of z. So this x2 of z was minus r naught upon r naught minus 2z. Now what we will do, we'll multiply by 2z whole inverse or minus 2z whole inverse on both the sides. So minus 2z inverse minus 2z inverse. So numerator and denominator will multiply it by minus 2z inverse. So what do we get here? We get r naught by 2 z inverse upon 1 minus r naught by 2 z inverse. Okay, and for this, what was our region of convergence? The region of convergence was magnitude of z greater than r naught by 2. Okay, so this was our region of convergence. Now again we can write it in our standard forms, or we'll try to write it. So we have r naught by 2 like this, once a minute, 1 minute, into z inverse into 1 minus 1 upon 1 minus r naught by 2 z inverse. Now again, if we look at this particular thing, this is of the form a 1 upon 1 minus az inverse with magnitude of z greater than a. Same form, and this has an inverse z transform of a power n into u of n with a as r naught by 2. So therefore, what we have is 1 upon 1 minus r naught by 2 z inverse has an inverse z transform of r naught by 2 to the power n z in u of n. Now if I multiply it by r naught by 2, then I'll get simply r naught by 2 to the power n plus 1 into u of n. And now again we have r naught by 2 z inverse getting multiplied. So same thing what we did here. So we'll use this time shifting property. So we'll shift in time domain by n naught, and here n naught is again equal to 1 because we have z inverse. So this is r naught by 2 to the power n plus 1, n minus 1 plus 1 u of n minus 1. So this comes out to be equal to r naught by 2 to the power n minus 1, sorry, n into u of n minus 1. So what do we have? We have x2 of n as r naught by 2 to the power n into u of n minus 1. So therefore, we have x3 of n as x1 of n plus x2 of n. What was our x1 or x2 of n? x2 of n was r naught to the power n into u of minus n. r naught to the power n into u of minus n plus x2 of n is r naught by 2 to the power n into u of n minus 1. So what we can do is we can take out this r naught to the power n common. Then we have u of minus n plus 1 by 2 to the power n into u of n minus 1. And this is our final answer, that is x3 of n. Is it clear? Any questions? So this was the last question that I planned to cover today. If you have any questions, then let me know.
Show me the time shift property formula, ma'am. Okay, ma'am.
Yeah.
Ma'am, there was some interruption in my side, so I missed question number 7. Can you just show it so that I can take the screenshot?
You will get the slides. Don't worry. You will get the slides and recording of this lecture, so you can see them that in detail. Still, I'll just show you once. Yeah, this is a big question, so you just see in the slides. I'll just share it in 10 minutes after this meeting is closed. You can open the portal and see.
Okay, after 10 minutes it will be shared.
Yeah, yeah. I'll upload it
Okay
and
then.
you can find it in the drive link.
Okay, ma'am.
Yeah. In fact, you can see this video recording after maybe 1 hour. I'll upload that also.
Okay, ma'am. Thank you so much.
Yeah. Okay. If you don't have any other questions, you can leave the meeting.
Okay, ma'am.
Yeah. Thank you for attending today's session.